Hello friends, I am Dr. S.P. Patil. In last two videos, we discuss about the piezoelectric method and magnetostriction method, which is used for producing the ultrasonic waves. Okay, now in this video, we discuss about the application of ultrasonic waves and also we discuss the dielectric parameters. Okay, so the objective of this video is to understand and study the application of ultrasonic waves in various fields and dielectric parameters. Okay, so first we talk about the application of ultrasonic waves. So first we'll discuss the industrial application. So first industrial application is drilling. So it is generally used for metal drilling. It is also used for making drilling plastics, rubber, etc. So you just keep in your mind for drilling purpose or metal drilling purpose, the ultrasonic waves were used. Now second industrial application is for soldering purpose, means to solder the different types of materials like aluminium or metal sheets, the ultrasonic waves were used. Now third industrial application is welding. So the ordinary welding is very difficult to weld the plastic type materials. So ultrasonic waves are used to form plastics and metals. So you just keep in your mind for welding purpose the ultrasonic waves were used. Okay. Now the fourth industrial application is cleaning. So we know that the ultrasonic waves have very high frequency, and due to this reason these ultrasonic waves used for cleaning small machine parts. Again it is used for washing clothes, in electronic devices, for jewelry cleaning purpose, the ultrasonic waves were used. So these are the industrial application of ultrasonic waves. Now next application, that is medical application. So in medical application, the first application is sonography. So this method is used to determine the pulse and blood flow in the veins. So for particularly this determination of pulse and blood flow in the veins, the ultrasonic waves were used. Now second medical application is photocardiography. So this photocardiography measures pumping sound of heart. So it is used for recording waveform of heart is known as a photocardiogram. So for photocardiography, the ultrasonic waves were used. And third medical application, that is this ultrasonic waves used for surgery purpose. So it is used for brain surgery. This method is generally preferred because the accuracy is high and very less chance for any damage of brain. So these are the medical application of ultrasonic waves. Okay. Now next we'll discuss the scientific application. So first scientific application is sonar, that is sound navigation and ranging. So it is used to determine distance of the object present in the sea by using this formula. D is equal to Vt divided by 2. Understood? So by using this formula we can determine or calculate the distance of the object which is present in the sea. Understood? Now second scientific application is echo sounding. So it is used means ultrasonic waves having very high frequency and low wavelength, that waves used to determine the depth of the sea, and that is nothing but the echo sounding. Understood? Now next application, that is chemical application. So in chemical application, first application is there. It is used for preparation colloidal solution of two different liquids. Second application, it is used to break the chain of polymers. It is used to measure the viscosity. So these are the application, chemical application of the ultrasonic waves. Now next, communication application is there. Now first communication application is ultrasonic waves used for echo depth sounding. Second communication application, it is used for the detection of submarines, iceberg and other object which is present in the ocean. Now third communication application, it is also used for the detection of aircraft. So these are some communication application of ultrasonic waves. Now next application, that is engineering application. Now in engineering application, first application is there, that is non-destructive testing. So the defect such as cracks detected by reflection of the waves at the interference of the object, this is done without damage to the crystal under test. Understood? Non-destructive testing means if there is any defect in the object like a cracks, okay, that cracks can be detected by using this non-destructive testing. So this is the first engineering application of the ultrasonic waves. Okay. Now second engineering application, that is thickness measurement. So thickness of the crystal calculated by using the formula velocity into time divided by 2. So by using this formula we can determine or calculate the thickness of the crystal. Now third engineering application, that is cavitation. So already in last video I discussed about the cavitation. One more time I will tell you what is meant by cavitation. So cavitation is nothing but when ultrasonic waves transducer placed in the liquid, then it produces the ultrasonic vibrations in the liquid. That means it produces the bubble in liquid, and that is nothing but the cavitation bubbles. Okay, the lifetime of that bubble is very short and then it collapses. This effect is nothing but cavitation effect. So these are the applications of the ultrasonic waves in various fields. Now we discuss about the dielectric materials. Okay, now dielectric materials. Okay, so first introductory part we'll discuss the insulating materials in which all the electrons are tightly bound to the nucleus of an atom called as a dielectrics. Okay, now all dielectrics, listen carefully, all dielectrics are insulator, but all insulators are not dielectrics. Okay, band gap of dielectrics are very high and electrical conductivity is very low because there are no free electrons available for the conduction. So these dielectric materials classified into two types based on the polarization. So first type is polar molecule and second one is the non-polar molecule. Okay, now see, in polar molecule the permanent electric dipole is there. In non-polar molecule the induced electric dipole is there. Now second thing in polar molecule, that is these polar molecules is dependent on the temperature, but this non-polar molecule is independent on the temperature. Okay, or simply we can say that here at the right side of the slide the polar and non-polar structures are there. Okay, now if you see the figure of polar molecule, so one end of the molecule is slightly positive. Here the example of the polar molecule is H2O. Hydrogen 2 atoms are there and oxygen 1 is there. Okay, so what happen in polar molecule, one end of these molecules is slightly positive, that is hydrogen having positive charge, and one end having charge is negative. So this is the structure for the polar molecule. Okay, now if we see the second figure, that is non-polar molecule, the hydrogen, that is H2 molecule is there and is an example of the non-polar molecule. Here what happen, the molecule of elements sharing electrons equally, and hence it is called as a non-polar molecule. Hydrogen, nitrogen, oxygen, all these are the example of the non-polar molecule. And the polar molecule having other examples are CO2, SO2. These are the examples of the polar molecule. Understood? Now next we'll discuss the properties of good dielectric material. Now first property, it should have high resistivity to reduce the leakage current. Second property, it should have high dielectric strength. Third one, it should have high mechanical strength. Next one, it should have high fire resistance. Then low thermal expansion. Again, these good dielectric materials have high thermal conductivity. Again, these materials have low dielectric loss. And last property of the dielectric material is it should have low water absorption quality. So these are the properties of good dielectric materials. Now here this slide shows some dielectric parameters are there. Now first dielectric parameter is dielectric constant, or it is also known as a relative permeability. Okay. Now definition of this dielectric constant is the ratio of absolute permittivity to the permittivity of free space. Okay. Here we can see dielectric constant is equal to relative permittivity, and this dielectric constant is denoted by letter K, and relative permittivity shown here, that is epsilon r. Okay, and which is equal to epsilon m divided by epsilon 0. Now this epsilon m is nothing but the permittivity of the material, and this epsilon 0 is nothing but the permittivity of the vacuum, or we can say permittivity of the free space, and which is equal to 8.85 418,782 into 10 raised to 12 farad per meter. So simply this dielectric constant or relative permittivity is the ratio of permittivity of the material to the permittivity of the vacuum or permittivity of the free space. Understood? So here one more definition is there, which is in the form of the capacitance. So it is the ratio of capacitance when the space is filled with dielectric material to the capacitance in vacuum. Okay. Now here at the right side we can see Cm is equal to K into C0. Now here K indicates dielectric constant, and which is equal to we get Cm divided by C0. So Cm is called as a capacitance with material in between the electric plates, and this C0 represent capacitance with vacuum in between the electric plates. Understood? So simply we can say the dielectric constant is also represent in the form of the capacitance with the material in between the electric plates to the capacitance with the vacuum in between the electric plates. Okay. Now next, second dielectric parameter we can discuss, that is electric displacement. Now electric displacement is denoted by letter capital D. So it is nothing but charge per unit area called as a electric displacement. Okay. So we can write the equation for electric displacement, D is equal to epsilon 0 into E plus P, where epsilon 0 is nothing but the permittivity of free space, capital E represent electric field. Now this P indicates polarization density of electric material. So this electric displacement is charge per unit area, therefore it is measured in coulomb per meter square. Understood? Now next one, Third one, electric polarization. Now electric polarization, it is also known as a simply polarization. So it is the process of producing electric dipoles by an electric field is called as a polarization in dielectrics. Understood? Or simply it is the ratio of induced dipole moment per unit volume of the dielectric called as a electric polarization. So here see this figure, then it is observed that when electric field E is applied to this dielectric material consisting positive and negative charges. Understood? Here E represent the electric field, positive charge, negative charge. Okay. Now when electric field E is applied to this material consisting or having the positive and negative charges, the negative charge moves opposite to the direction of the field. That is, this negative sign moves this side, that is left side, which is opposite to the applied electric field, while this positive charges moves in the direction of the field. So the charges displacement creates dipoles in the material called as a polarization. Understood? Now last definition or dielectric parameter is polarizability. Now when a dielectric material is placed in an electric field, the displacement of electric charge gives rise to the creation of dipole in the material. Then the polarization P of an elementary particle is directly proportional to the electric field strength E, capital E. So we can write the equation P is proportional to E. Here we can see first equation, P is proportional to capital E, and which is nothing but P is equal to alpha into E. Here this alpha is nothing but the polarizability constant or proportionality constant. Okay. Now it is measured in farad meter square. Okay. If the dielectric material contains n number of dipoles per unit volume, then we can write this equation like this: P is equal to capital N into alpha into E. Okay. So one more time, again we will discuss the application and dielectric parameters. Okay. Now application of ultrasonic waves. So first, industrial application. There are 4 industrial application: drilling, soldering, welding, cleaning. So for metal drilling purpose, the ultrasonic waves were used. For soldering purpose, if suppose to sold any metal sheets, so the ultrasonic waves were used. That means for soldering purpose also the ultrasonic waves were used, or simply for or to solder the different types of material like aluminum or metal sheet, ultrasonic waves were used. Now third industrial application, that is welding. To weld the metal sheets or plastics, the ultrasonic waves were used. Now cleaning. We know that the ultrasonic waves have very high frequency, and due to this reason, this ultrasonic waves used for the cleaning purpose. So to clean the small machinery parts, again it is used to washing the clothes, again electronic devices, then jewelry cleaning purpose, this ultrasonic waves were used. So these are the industrial application of ultrasonic waves. Now next, medical applications are there. Now first medical application, sonography. So for sonography purpose, now in sonography it is used to determine the pulse and blood flow in the veins. The ultrasonic waves were used. Now second medical application, that is photocardiography. Now in photocardiography it measures pumping sound of heart. It is used for recording waveform of heart. Waveform of heart is known as a photocardiogram. And third medical application, that is in surgery. For surgery purpose, the ultrasonic waves were used. Now in surgery, it is used for brain surgery. Okay, and this method is generally preferred because the accuracy is very high and very less chance for any damage of brain. So these are some medical application of ultrasonic waves. Now next, scientific applications are there. First scientific application is sonar, that is sound navigation and ranging. So in sonar, the distance of the object which is present in the sea can be calculated, and that can be calculated by using the formula D is equal to Vt divided by 2. Now second scientific application, echo sounding. It is used to determine the depth of sea. Now next applications are there, that is chemical application. Now first chemical application, it is used for preparation colloidal solution of two different liquids. Then second chemical application of ultrasonic waves is used to break the chain of polymers. So third chemical application, it is used to measure the viscosity. So in all chemical applications, the ultrasonic waves were used. Now next application, that is communication application. Now first communication application, that is it is used for echo depth sounding. Now second communication application, it is used for the detection of submarines, iceberg and other object which is present in the ocean. Now third communication application is, it is also used for the detection of aircraft. Now these are the communication application of ultrasonic waves. Now next, engineering applications are there. Now first engineering application is non-destructive testing. The defect such as cracks detected by reflection of the waves at the interference of the object. This is done without damage to the crystal under test. That means simply, suppose if there is any defect like crack in the object, that crack can be detected by using this non-destructive testing. And in this non-destructive testing, the ultrasonic waves were used. Okay. Now second engineering application, for thickness measurement, the ultrasonic waves can be used, and that thickness measurement of the crystal can be done by using the formula Vt divided by 2. That V is nothing but the velocity and T is nothing but the time period or time. Okay. Now third engineering application is cavitation. When ultrasonic waves transducer placed in the liquid, it produces ultrasonic vibrations in the liquid. That means it produced the bubble in the liquid and called as a cavitation bubble. Okay. The lifetime of that bubble is very short, and then after that or after some time or after their lifetime, they collapse, and that effect is known as a cavitation effect. So these are the applications of the ultrasonic waves in various fields. Okay. Now next part we'll discuss about the dielectric materials. Now already I have told you, dielectric means what? The insulating materials in which all the electrons are tightly bound to the nucleus of an atom, called as a dielectrics. So all dielectric materials are insulator, but all the insulators are not dielectrics. Band gap of dielectrics are very high, but electrical conductivity is very low because there are no free electron available for the conduction. Understood? So there are two types of dielectric material which is based on the polarization. So first one is the polar molecule and second one is the non-polar molecule. Now in polar, the permanent electric dipole is there. In non-polar molecule, induced electric dipole moment is there. Now second difference in polar molecule, its polarization is temperature dependent. Now second difference in non-polar molecule, that is its polarization is independent on the temperature. Understood? So simply we can say, or at the right side of this slide we can show or we can see two figures are there, one for polar molecule and other one is for non-polar molecule. If we see the figure for polar molecule, then it is observed that H2O structure is there, H2O, water structure is there, two hydrogen atoms are there and one oxygen atom is there. Okay. So polar molecule means what? One end of this molecule is slightly positive. Here we can see hydrogen having positive charge. Okay. And other end, or we can say one end is slightly negative, that is oxygen having negative charge. So this is nothing but the polar structure. Okay. Other examples are CO2, SO2, etc. Now here second figure shows non-polar molecule. Now in non-polar molecules, that means molecule of element sharing electrons equally, and that is called as a non-polar. Here we can see the example of the hydrogen, H2. Okay. Now H2, another example of the non-polar is O2, N2, F2, all these are the example of the non-polar molecule. Understood? Simply you just keep in your mind, polar means what? The one end of this polar molecule is slightly positive charge and other end having negative charge. That is nothing but the polar molecule. And non-polar means what? In non-polar molecule, the element share electrons equally, and that is called as a non-polar. Understood? Now these are some properties of the dielectric material. So first property, it should have high resistivity to reduce the leakage current. Second, it should have high dielectric strength. Third, it should have high mechanical strength. Fourth, it should have high fire resistance. Next, it should have low thermal expansion. Next property, it should have high thermal conductivity, low dielectric loss, and last property of dielectric material, it should have low water absorption quality. So these are the properties of the dielectric materials. Now next we'll discuss about the dielectric parameters. Now there are four dielectric parameters. First one is the dielectric constant, or it is also called as a relative permeability. Okay. So definition of this dielectric constant is, it is the ratio of absolute permittivity to the permittivity of the free space. Okay. Now at the right side we can see the dielectric constant is called as a relative permittivity. This dielectric constant is denoted by letter K and relative permittivity is denoted by epsilon r. So K is equal to epsilon r is equal to epsilon m divided by epsilon 0. Epsilon m indicates permittivity of the material, epsilon 0 indicates permittivity of the vacuum, and which is equal to 8.85 into 10 raised to 12 farad per meter. Okay. So simply this dielectric constant is the ratio of permittivity of the material to the permittivity of the free space. Understood? Now another definition is there which is in the form of the capacitance, that is, it is the ratio of capacitance when the space is filled with the dielectric material to the capacitance in vacuum. Again at the right side we can see here formula Cm is equal to K into C naught. Here this K is dielectric constant, C naught indicates capacitance with vacuum in between the electric plates, Cm indicates capacitance with material in between the electric plates. So the dielectric constant is the ratio of capacitance with material in between the electric plates to the capacitance with vacuum or free space in between the electric plates. Okay. Now next definition, electric displacement. So this electric displacement denoted by letter capital D, and very simple definition is there. It is the charge per unit area called as a electric displacement, or here I will read, it is the charge per unit area that would be displaced across the layer of conductor placed across in electric field. So we can write electric displacement D is equal to epsilon 0 into E plus P, where epsilon 0 is nothing but the permittivity of free space, capital E represent electric field, P denotes polarization density of electric material. Okay. So if this electric displacement is charge per unit area, its unit is coulomb per meter square. Understood? Now next we'll discuss about the electric polarization, or simply we can say that polarization. So it is the process of producing electric dipoles by an electric field called as a polarization in dielectrics, or other definition, it is the ratio of induced dipole moment per unit volume of the dielectric called as a polarization. Okay, by mistake the diagram is in before pages is there, that is, here we can see when we apply the electric field to this dielectric material consisting positive and negative charge, okay, then it is observed that these negative charges or negative charge move opposite to the applied electric field, and this positive charge moves in the direction of the applied field. So the charges displacement creates dipole in the material and called as a polarization or electric polarization. Okay. And last parameter, that is polarizability. In polarizability, when a dielectric material is placed in an electric field, the displacement of electric charge gives rise to the creation of dipole in the material. The polarization P of